Hi, in this talk I will speak about scheduling and discrepancy. More specifically about a connection between minimizing flow time and the prefix discrepancy in the so-called Beck-Fiala setting. This is joint work with Nikhil Bansal from University of Michigan and Svensson from EPFL. My name is Lars Rohwedder and I've recently moved to Maastricht University. So what is flow time? Flow time is the time between a job's arrival or release time and the time when it is completed. So naturally this objective has been studied a lot in scheduling and it's one of the classic measures for quality of service. At the same time there are many problems where it remains poorly understood. So many variants where we algorithmically do not have a full understanding of the problem yet. But on many of these variants there's been exciting progress recently. For example, if you look at the sum of weighted flow times on a single machine, then there's a recent line of work that leads to a constant approximation. The sum of flow times has been looked at on parallel identical machines, so multiple machines, and also on parallel unrelated machines, so that is the most general machine model. And in this parallel unrelated machines model, another objective that is very interesting and non-trivial is minimizing the maximum flow time. And of course, flow time is also very reasonable to look at in online models, and there are many exciting results there as well. In this paper, we look at the flow time objectives on unrelated machines, and we obtain new guarantees for both cases. And for this talk, I will focus mostly on maximum flow time, but many of the ideas apply in a similar, slightly more involved way also to the objective of minimizing sum of flow times. So let me formally introduce the problem. We are given a number of m unrelated machines and we are supposed to place jobs on them. So the colored rectangles here are the jobs and they are placed on some machines, which describes at what times they are executed. They can only be executed on one machine and they cannot be preempted, but we can choose when or where to place them. So one job is characterized by its processing times, Pij, and here it is noteworthy that since we are looking at the unrelated machine model, the processing time is different or can be different on each machine. So this is the processing time of job J on machine I, and this could be very different on another machine. So if I place this same job on machine 1, it might have a different processing time. A job also has a release time, and if you're given a release time and a schedule, then you can figure out the flow time of a job, which is the time between release and its completion. And like I said before, the case that we are looking at here is to minimize and then maximum over all flow times of all jobs. So maybe more famous is even this special case here when all jobs are released at 0. In that case, the maximum flow time is the same as the maximum completion time or the maximum machine load. And it has been known for 30-40 years that for this problem you can find a 2 approximation, and this was discovered by Lenstra, Moyes and Tardush. And very briefly explained, their argument is as follows. They set up an LP with assignment variables xij. So xij describes whether job j is assigned to machine I, and well, in total these xij's must be 1 for every job, and apart from that you have another constraint for each machine which says the load on this machine must be at most whatever make span you would like to achieve. And If you count the number of constraints and the number of variables, you will notice that the number of constraints is fairly small, which then leads to very sparse extreme points. So if you take an extreme point solution of your linear program, then it has very few non-zero variables. This makes it much easier to round the solution, and it turns out that with a few other very beautiful tricks you can round all variables, incurring only an additional error of opt. So you get a total makespan of opt plus opt, which is 2 opt, and that's great. It's a constant approximation, and we would really love to have the same for a maximum flow time. So why does this argument not work in maximum flow time? Well, it turns out that what you need are constraints for all intervals and all machines. So if you look at some interval, for example, between time t1 and t2 on some machine, and you look at all jobs that are assigned to this machine and released inside this interval, then it's not hard to see that the sum of these processing times, so the total volume of these jobs, must be at most length of the interval plus Fmax. So Fmax is the maximum flow time that you want to guarantee for every job. Because if you didn't have that, if your total processing time of these jobs was higher, then well, one of these jobs must be completed after T2 plus Fmax, and since it is released before T2, it would have a flow time of more than Fmax. So these type of constraints, they are certainly necessary, but it turns out they are also sufficient. So if you can find an integer solution with these types of constraints for a small value of Fmax, then you're done. And well, what Bansal and Kulkarni, who gave the best approximation algorithm previously to our work, what they had done was they wrote an LP with exactly these type of constraints and assignment variables similar to the makespan case. Then, well, what you get is a solution that is much less sparse, because the LP has constraints for all intervals, which are much more than just having a constraint for every machine. And they still managed to round these extreme points, but it turns out that they could only round half of the variables at an error of order of opt. So they have to repeat this log n times to round all the variables, and that's where they lose the log n factor, and that's why their approximation rate is log n. And intuitively, this seems like a very tough barrier to break, because if you cannot round all the variables, then it seems very hard to need much less than log n rounds. At the same time, in each round, since you are rounding some variables, you will get some error, and getting that to less than constant times opt also seems not plausible. So this is a very natural barrier that seems very hard to avoid. But we will use completely different techniques, and we will actually manage to get something better than that. And these techniques, they will be borrowed from seemingly completely different problems. So to do that, it will be useful to introduce this seemingly different problem. And let's start with the Beck-Fiala theorem, which is one of the classical theorems in discrepancy theory. And I state it here in a variant that is convenient for me to use later on, and the variant is as follows. We have vectors v1 until vn in some dimensional space. It doesn't matter the number of dimensions. What is important is that the L1 norm of each vector is at most t. So that means if you sum up the absolute values of all the components for one particular vector, then the sum is at most t. The theorem says you can find signs epsilon 1 until epsilon n, which are either -1 or 1. And if you now take the signed sum of your vectors, so you multiply sign 1 with vector 1 at sign 2 times vector 2 and so on, you sign them all up, then you get a total vector, and this vector will be, or you can find these signs such that this signed sum is very small in every dimension, and the bound that they get is order of t. So let me briefly sketch how they achieve this, really again leaving out all the details, but the basic framework is they set up a natural LP relaxation where every sign can be between -1 and 1 and not necessarily integral, and then they exploit that this system of linear equations has very few constraints. They can use that to find a sparse extreme point solution, so an extreme point where many of the variables are already -1 or 1, and then they can round the rest and round all the variables inducing only an error of, oh, this is supposed to be order of t, not opt, but they round all the variables and get only order of t as a final discrepancy. And well, so this should look familiar to you, of course. This is very similar to Lenstra-Schmois-Tausch, at least on a high level. And also here we will look at a generalization, and the generalization is called Prefix Beck-Fiala. And here input is the same, but you want something stronger. You want to find signs so that not only the signed sum of all the vectors is small in every dimension, but if you take any interval of vectors, so the vectors are ordered and you take some h smaller than L, and you take the signed sum of vectors only between h and L, then you want also a good bound here. And the important thing here really is that you want to find one coloring or one set of signs that is good for all intervals simultaneously. And well, you can quite easily prove bound of order log n times t for this problem, and you can probably guess the basic idea here. You set up an LP which has constraints for all intervals, so this is a lot more constraints than we had before, which turns out, which leads to an extreme point solution that is not as sparse as before, but we still manage to round half of the variables at an error of order of t, and we repeat this log n times so that all variables are, or all signs are -1 or 1, and this leads to a discrepancy in the end of order log n times t. Well, these four problems, we see the same wall. We hit the same wall. It seems very hard to avoid this factor of log n that we lose in the more general variant in both problems. But of course this is not the end of the story, because there is a great hammer for the Prefix Beck-Fiala setting. Because what I just showed you is not the state of the art for Prefix Beck-Fiala, but perhaps surprisingly there is a better bound for this. Namely, an ingenious theorem by Banaszek, who proved that you can get bound order square root log n times t for Prefix Beck-Fiala. And this theorem is proved in a completely different way, using very deep ideas from convex geometry. And this Prefix Beck-Fiala setting is not even the most important application of his techniques. Even more famous is that his proof also gives the best bound towards the Komlosh conjecture. And of course I cannot explain this proof here, but just to give you a very quick idea where the square root log n comes from, his proof is based on using convex bodies with a high Gaussian measure. And if you take a hypercube, which corresponds kind of to the maximum norm, so the maximum discrepancy over all dimensions, if you take a hypercube centered at 0, then square root log n is kind of the edge length where from where your Gaussian measure of this object goes from very low to very high. So in order to get a very high Gaussian measure, which he needs to consider hypercubes with edge length square root log n, or order of square root log n. And that's where the square root log n comes from, and this is also very inherent in his proof. Still, it's absolutely amazing that this improves over the, well, easy extreme point kind of argument. So for the remainder of the talk, we will borrow these methods to also get better guarantees for our scheduling problem. At the same time, I think there's also things that are interesting for discrepancy theory. Namely, our scheduling application, it then motivates also new questions in discrepancy theory, which seem to be non-trivial and which definitely would seem to be very interesting, maybe slightly novel variants of questions in discrepancy theory. So let's start with an easier task. Of course, in the end we want to round an arbitrary LP solution, but let's start with a half integral solution. So every job is assigned to 2 machines, and it's assigned 50% to one machine, 50% to 2 machines. So in this picture again, the boxes are the jobs where they are scheduled, and each color corresponds to one job, and each job is split between 2 machines. The reason, if you wonder why the boxes have different sizes on the different machines, is simply because we are under unrelated settings, so the processing times are not the same. So this means even scheduling 50% of the job on machine 1 might be very different from scheduling 50% on machine 2. So a natural thing to do when you want to round this half integral solution is to consider 2 options. Well, you could either completely move the job to the first machine where it is partially assigned to, so basically increase the load on the first machine by 1/2 times the job's processing time, and reduce on the second machine the load by 1/2 times the job's processing time. Or you can do the opposite, so decrease the load of the machine of the first machine by half of the job's processing time, and increase the load on the second machine by half of the job's processing time. So another way to phrase this is we can build up a vector which has a component for every machine. So this vector corresponds to this purple job, and we put a value of 0 in every machine where this job is not currently assigned to, and for the 2 machines where it is half assigned to, we will put in 1/2 of the job's processing time, and one of the 2 components we will negate. So if you just look at rounding this particular job, and you look at how the loads on these machines change, then the option is really to either add this vector or subtract it. So this already looks familiar, so we are supposed to find a sign for this vector, so that looks a lot like discrepancy. So let's just quickly recall what we need for minimizing the maximum flow time. Well, we had these constraints for every interval of time, and we looked at all jobs that are released in this interval, and we require some upper bound on the total processing time of these jobs. So if we increase this bound, then the maximum flow time increases by the same. So since we are dealing here with intervals of time, but then inside an interval we always look at the jobs released there, we can actually emulate this here by setting up the vector for every job and then sorting them by release time. Because if we now apply a Banach check, we get some bound on how every interval changes, and these intervals, since we ordered by release times, they actually correspond to intervals of jobs released in some time. And applying Banach check to these vectors that we construct in this way, we find out that we can get signs so that the load increases on each interval by at most the maximum of the Pij times square root log n. And why is it the maximum of the Pij's? Because these vectors that we have here are each bounded in L1 norm by the maximum of Pij. And so of course these signs then tell us where to assign the job. So if it's positive, in this case, so for this vector, if the sign is positive, I assign it to machine 1, and if the sign is negative, I assign it to machine 2. With a little bit of care, you can easily make sure that the maximum of the processing times is essentially bounded by opt, so by the maximum flow time. And this means that the error that we induce is only opt times square root log n. And it's important to note that here we are now rounding all the jobs at once, and we only get an error of square root log n instead of getting order of log n. So because opt is the maximum flow time, the maximum flow time increases with this rounding only by a factor of square root log n. However, we assumed in the beginning that we are already given a half integral solution. So how do we do it in general? In general, we don't have a half integral solution, but we have an arbitrary fractional solution. But the same trick here can be applied in a slightly more general way as follows. Consider 1 over 2 to the h integral solution. So that means every job is split into 2 to the h equal pieces, and these are all assigned to a machine each. And now our goal is not to round it completely, but we just want to get a less fractional solution. So we want to reduce these 2 to the h pieces to 2 to the h minus 1 pieces. So every job we basically reduce the number of pieces by 1/2. And this can be easily done with the same trick. What we first do is we pair up the pieces of jobs, and now you can consider just every pair of jobs, every pair of pieces as a single job. So for example, the red job is now not 4 pieces, but you have 2 red jobs of 2 pieces each. So this is kind of just a half integral solution, where the integral solution would assign every pair integrally. So you just apply the same half integral rounding as before, and what you get is an error of maximum Pij divided by 2 to the h times square root log n. So why is that? Because since we split every job in 2 to the h pieces, the processing time, or the maximum processing time, also reduces accordingly. So if you start with a very fractional solution, so that means h is very large, and you just repeat this over and over again until you get to an integral solution, you just have to sum up these errors for all h, and this of course is just a geometric sequence which in total is also bounded by a maximum of the Pij's times square root log n. So this then leads to our result that the integrality gap the for this natural linear programming relaxation with constraints for all intervals and assignment variables, that this linear program has an integrality gap of at most square root log n. So to conclude, what we show in this paper is that the integrality gap of the natural LP relaxation for max flow time is at most square root log n, and we also study total flow time or sum of flow times, and here we show that the integrality gap of an LP that's called the time indexed LP, that this time indexed LP has an integrality gap of at most log to the 3/2 n. This is against the lower bound that is known of square root log n. So both of these theorems are within square root log n within the optimum. I'm saying integrality gap because what I didn't say before is that our results are not constructive. The ingenious proof by Banaszek, it does not lead to an efficient algorithm, unfortunately. So so far we cannot get a true approximation algorithm out of it. We just get a bound for the integrality gap of the linear programming relaxations in each case, and this could also be used, for example, for an estimation algorithm that just estimates the optimum but doesn't construct the solution efficiently. So I think our result it opens a few interesting directions. Well, one of them is surely not new, but it gives even more motivation to making Banaszek's proof constructive. This would be, I mean, this if you had it constructive, it would immediately mean that we get the same guarantees as in a polynomial time approximation algorithm. Another interesting direction is, well, you could say, okay, both of these bounds are within square root log n from the lower bound. So could you get even better? Well, the answer is yes. If you could prove order of t for prefix Beck-Fiala, so recall that in the normal Beck-Fiala discrepancy you can show order of t, and at least with current knowledge it would be consistent if you could improve Banaszek to order of t. And if you could do that, you would immediately get better bounds. Well, you get tight bounds up to constant for both of these cases of flow time. So in general, there it might be worth even looking at the specific discrepancy instance that we construct. So for example, the type of vectors that we get only have two positive entries, or they only have two non-zero entries. So the case of prefix discrepancy that we need here is even more specific than the Beck-Fiala setting. So this might motivate even this seemingly simpler case of discrepancy. Well, this is all that I want to say here, and I hope to see many of you in Rome at STOC, and goodbye.